So, what we talk about today, there's one aspect of what we talk about today of simple harmonic motion that really confused me when I was learning it, and so that's what I'm going to emphasize, and I created a little simulation to kind of show that concept. Before we really start digging into it, I just want to remind you that the study of simple harmonic motion, while seemingly rather mundane at the AP Physics 1 level, because we really just talked about springs going back and forth and pendulums swinging back and forth, the actual physics, and specifically the mathematics that describe the physics, are then used as you progress in your study of science and physics to then describe wave motion. Wave motion could be a wave on this guitar string, right? You pluck a guitar string and it's the wave motion of the guitar string that then vibrates the air molecules around it that make wave motions travel through the air, which creates sound at a certain frequency, which tells you the pitch. Light, as we'll learn next year in Physics C when we do electromagnetism, light is an electromagnetic wave. That wave motion is described by the wave equation, the equations that describe wave motion. If you're going to become a physicist, you're going to become an expert in quantum mechanics, which is the most modern, the most recent development in science. When you're talking about quantum computing and the newest TVs and the newest phones and the newest technology, it's all dealing with quantum physics to make things operate more efficiently, to get transistors smaller. And if you know anything about quantum mechanics, one of the main features of it is that on the subatomic level, subatomic particles do not behave like particles as we experience them in day-to-day life. An electron is not a little ball that moves in an orbit around the proton in a hydrogen atom. Like, it's not remotely like that. The mechanics of how subatomic particles move are much more accurately described using wave mechanics, quantum mechanical wave mechanics. And so the mathematics that we start developing when we start understanding simple harmonic oscillators like masses attached to the ends of springs will then go on. Obviously, it'll build and it'll get more complex and more rigorous, but then you'll use the same foundation to describe like the electron motion in an atom or just anything on the subatomic realm. So it's very important for those of you that are going to be engineers, because you're going to have to do modern physics in college if you're going to be an engineer. Those of you that are going to be a physicist, obviously you're going to have to learn all this. But this is the starting point. This is the starting point of all the units that we've done so far. Newtonian mechanics, very important to understand. In modern physics, though, Newtonian mechanics isn't used quite so much as like wave mechanics and quantum mechanics and relativity, right, at the higher levels. Okay. All right. So it's very important, very important. The simple harmonic motion is the foundation from which you build a huge amount of further knowledge after you learn it. So it's important to understand what's going on. So just to remind you, simple harmonic motion, you compress the spring, you get a spring force. That spring force is at a maximum when the object is at its maximum displacement. Maximum force, by Newton's second law, tells us we have the maximum acceleration. Yet we release this object from rest, it has a velocity of 0. So when it has a maximum acceleration, it has a velocity of 0. But we have started from our maximum displacement, in this case negative displacement, right? And then we let the guy go. And then eventually he comes to the equilibrium position. When he gets to the equilibrium position, he's moving at maximum velocity because we had a force act on it throughout that whole interval, increasing its velocity. Now the force decreases, so the increase in velocity happens at a smaller and smaller amount until it gets to this point at equilibrium. At that instant, there is no force. So at that instant, there is no acceleration. So we're in a position of 0. We always measure positions in harmonic oscillators from the equilibrium position. So a position of 0, maximum velocity, but again, 0 acceleration because there's 0 force. Yes, sir?
Wait, so that position, the kinetic energy is the highest, right?
Yes, sir. Okay. Yep. Kinetic energy is the highest. The spring potential energy is 0. Yep. And then it just carries through, and then it reaches the positive amplitude, at which point the kinetic energy is 0, and the potential energy is maximum, right? And then we have a maximum negative acceleration because now it's pointing to the left. And maximum force, maximum acceleration, magnitude, talking magnitudes here. Maximum displacement, but 0 velocity, right? So it's kind of counterintuitive. When it's maximum acceleration, you have 0 velocity. When it's maximum velocity, you have 0 acceleration, And the positions are easy to see because you're talking about the two amplitudes and equilibrium. Okay? All right. So you got to understand that. We've already talked about all that stuff. I'll give you a more graphical depiction of the actual motions in terms of position, velocity, and acceleration later today. But for now, I'm going to define some new vocabulary that is essential to understand when talking about simple harmonic motion. We're not going to focus on energy today. We're going to focus on other aspects of simple harmonic motion. And so that's going to be the vocabulary that I'm going to give you right now. This is all in the notes, by the way, that I gave you yesterday, that you picked up yesterday. It's all in that set of notes I gave you. So the first thing is amplitude. Amplitude, in a mathematical sense, gets the symbol capital A. If we're looking at our simulation here, move it towards... Got to move it so the folks at home can see without the glare. Oh, come on. So here, this is my equilibrium position. And I do work on the object to push it to the side, storing energy. This position I would call the negative amplitude, because it's on the negative, in the negative direction. The x that goes in our Hooke's law and energy equation, spring potential energy equation, is this, that vector, drawn from the origin, our origin in our coordinate system is the equilibrium position. And it is, in fact, equal to negative A at that location. Okay, that is the amplitude, right? And then I hit play, and I can wait for it to get to the other amplitude. Right about there. Oh, wait. Oh, something's weird. Hold on. Oh, dang it. Who did this? Kurt, this was you. Oh, Kurt. Okay, now it'll work. Sorry, let me do that again. I'm going to compress the spring. First, I'm going to label the equilibrium position. This time I'm going to verify that's equilibrium by hitting play and making sure it's not moving. It is not. Good. Then I compress the spring a certain distance, and I can indicate the position of the mass with a position vector, x. At that position, the mass is at the negative amplitude, because it's to the left. Then I hit play, and then it will move to the positive amplitude. So its position, I use the position vector x to describe its location, and at that particular location, it's at the positive amplitude. The amplitude is self-explanatory, so I'm not going to write anything. Okay, the amplitude is literally the maximum displacement from equilibrium. Those in pre-cal or have taken pre-cal, this amplitude, if we were to describe the position of this object versus time on a motion graph, you'd get a sine graph or a cosine graph, depending on where you start. The amplitude of a sine graph, you put a line right down the middle of it. The maximum amplitude is how high above the equilibrium line you go. The negative amplitude is how far below. But it's the same distance, right? Same distance here, same distance there. The amplitude is just the maximum distance from equilibrium. Okay. All right. That's not new. That's not new. This next one will be somewhat new, and that is the period. And since period starts with a capital T, the symbol for period is a capital T. This I'm going to define because it's very important to understand. The period is the time required for one complete oscillation. Sometimes they say oscillation or cycle or back and forth motion. The time for one complete cycle is the period. Since it is a time interval, the unit is the second. So the unit is the second. Now I want to emphasize something here, because this can be somewhat confusing for some students. It's easy to see. I can calculate the period. I can start my timer whenever I release the mass. I can start it now. and then wait for it to come back and stop it. That's one period. Okay, not the time it takes to go from here to the other side. That's a half a period. A period is the time it takes to go from here and then back. And if I time that, I get a certain time value. If I start my timer, say at this position, right here, I'm going to wait for it to get back to its original position, right there. That's not the period, because it's moving the opposite direction. That is not one complete cycle. If it starts moving this way, one complete cycle, it's going to go there, and then back to this position. That's one complete cycle, right? And it's easy to see by saying, well, let me calculate the period from this position. If I start here, hit my timer, stop my timer, that's a much smaller time interval than it was whenever I did the whole cycle, right? And the period should be the same regardless of where you start your timer, okay? So to understand, the period is the time it takes to go from one position to the same position, but it must be moving in the same direction. So if I'm going to calculate the period from that location, I have to start my timer, and then wait for it to get back, but don't stop it here. I gotta wait until it gets back to that same position, but moving in the same direction. That, the time it takes for that complete oscillation is one whole period. Make sense? Make sense, Kurt? Okay. Go back. There we go. So that's the period. The next one is the frequency. Frequency actually starts with the letter, the first letter of it. It's the word, lowercase f. You guys remember? You don't remember. There's a thing called radio that operates on radio waves that are detected by antennas, and then you have to tune the dial on your radio in order to hear a certain radio broadcast from a certain radio station. Are you aware of these things? Yeah. Okay. So you had to turn into a frequency. Usually those frequencies are the numerical values are in the thousands, because radio waves, I don't know if you know this or not, radio waves are light waves, just like the light that we see coming from the lights in the ceiling. They're just really, really long wavelength, really low frequency light waves. That's why they're not dangerous. That's why you can be bombarded with radio waves your whole lives, which you always are, and not suffer any ill effects from them. So when you tuned into a radio frequency back in the day, you were actually tuning in to this type of a frequency. Only instead of a mass spring oscillator, you're tuning in to the oscillations of radio waves, light waves, that oscillated at whatever frequency the station was broadcasting them at. So it's very closely related to the period. The frequency is the number of oscillations / cycles per second. So if you have 4 complete mass spring oscillations per second, then the numerical value for that frequency is 4. That's simple. Okay. The unit is kind of weird. The unit is, you could say, cycles or oscillations per second. But those of you that truly understand your angle measurements, degrees and radians, you know that the degree or the radian isn't an SI unit of measurement. It's a placeholder unit, right? And so a radian you can actually just replace with one, and you can leave out the unit. So sometimes you'll see cycles per second as just 1/seconds, because the unit cycle is just a placeholder, okay? And sometimes 1/second, and I remember being confused with this when I started going back to college after taking a few years off after high school. I was seeing units like this, seconds raised to the -1 power, and that would confuse the crap out of me. So I just want to point that out in case you're going to be in the same boat that I was when you get to community college or college when you get there. Seconds to the -1 just means 1/seconds, and that can be interpreted as cycles per second. For this class, though, just think of frequency as number of oscillations per second, or number of cycles per second. Okay. there is a very definitive relationship between period and frequency. And let's talk about Wilbur here. Let's say that Wilbur goes around the circle. Oh, wait, hold on. I gotta. For the folks at home. Let's say Wilbur. Let's see. 1, 2. Let's say 2 cycles per. Let's say 2 seconds. Let's say the period of Wilbur, the time it takes. We talk about period of mass spring oscillators, but we can talk about the period of circular motion too. It's just the time that it takes for one complete circular motion. We talked about that actually. Remember the period from 2 pi over the period is the speed. So let's say that the period of Wilbur's circular motion is 2 seconds. What's the frequency? How many circles per second is he flying in? 1/2. It's 1/2. So 2 second period, 1/2 of a second frequency. Right? If it takes him 2 seconds to go around, he's only going to get through half of a circle in 1 second. What if the period was a half a second? What would the frequency be? Frequency is half a second, so it goes through. The period. The period is half a second. So if it takes half a second to go around once, how many times will it go around in 1 second? 2. So the frequency would be 2. So what's the relationship between the period and the frequency? They are, starts with an I?
Inversely.
They're inversely proportional. They're inverses of each other. So we could say, and I'll put this right here in red, period and frequency are related by this equation. For those of you that are good with your algebra, you know that you can write that equivalently that way. Right? So that's what relates period and frequency. That's not how it's written on the formula sheet. How it's written on the formula sheet will actually relate them to another quantity, and that's what I'm going to talk about now. And this is the confusing one. So the fourth new term and last new term for the day is what we call angular frequency. And there's another way that we say angular frequency that you'll see. They're synonymous. They mean the same exact thing. Angular velocity. And I'm just going to define this, and hopefully, if you're like me, the confusion will set in as I'm describing this. Because remember, we're talking about a mass spring oscillator that's oscillating back and forth on a spring. If you're like me, you're going to be confused as I give you this definition, but then I'm going to show you some simulations that'll hopefully dispel that confusion. And I forgot to go back with the camera. Sorry, those people at home. You didn't miss much, don't worry. Angular frequency. Angular frequency is the number of radians, and I'll say covered or swept out, covered per second. The units is very similar to frequency, but it's angular frequency. And again, if you see angular velocity mentioned, it's the same thing. The unit, instead of cycles per second, is radians per second. Oh, by the way, I forgot to say, cycles per second gets a special name. There's a definition. Something is defined in terms of 1 over seconds, or cycles per second. That's the 3 lines means defined as. What do you measure frequency in? Hertz. Yeah, who said that? Very nice. Hertz. Hertz, HD. And so we can talk about frequency in terms of hertz. And so that's what you would tune into on your radio frequency. If you're tuning into an AM band of like 1800, it's 1800 hertz. That means that every second you'd have 1800 cycles of light waves being detected by the antenna. Yes, sir.
So this is going way back, but is there any units for amplitude?
Meters. Yeah. The SI unit would be meters. Sometimes it's in centimeters, but then you'd have to convert it to meters to do the mathematics. Okay. So we can talk about, this is where it should get confusing if you're paying attention, the angular frequency of a mass that's oscillating back and forth in a straight line. Can you see where the confusion sets in? Like, I can talk about the angular frequency of Wilbur, or I can talk about the angular frequency on this particular simulation. I can talk about the angular frequency, or the angular velocity, I'll say angular velocity of this guy. Right? Obviously, the linear velocity is 3.75 meters per second. The angular velocity, though, let's say that it takes, I'm going to do radians here. We all know radians, right? Let's say it takes 1 second to go that far. What would you say the angular velocity is? Approximately, because I didn't stop it exactly at that.
Pi over 2.
Not pi, thank you. Yes, pi over 2.
You expected me to be wrong.
Was that not Jacob?
No, that wasn't it.
Okay.
You got it for me.
What's 90 degrees? You should all know this.
Pi over 2.
Pi over 2 radians. If it takes 1 second, to cover pi over 2 radians, then your angular velocity would be pi over 2 radians divided by 1 second, which is pi over 2 radians per second, right? And so throughout this motion, this object that is literally moving in a circle is covering pi over 2 radians per second. That's what its angular velocity would be. And as I said, we can also say that's the angular frequency, right? Those two words are interchangeable when we're talking about this stuff. The thing is, and again, the confusing part is this guy, not that one. This guy is not obviously moving in a circle. He's not moving in a circle. However, we still say that this system has an angular frequency. And again, if you're like me, that confuses you and it makes your brain hurt, which is why I'm going to fix that right now by just showing you a couple other simulations and animations. Turns out that if we take a mass spring oscillator and an object undergoing uniform circular motion, meaning constant speed motion in a circle, and we make sure that the two have the same period, then the vertical position of this mass will match the position of the mass here. The vertical component of the velocity of this mass will always match the vertical velocity of this mass spring oscillator. The vertical component of the acceleration of this mass will always match the vertical acceleration of the mass spring oscillator. So yes, this guy is not moving in a circle, but we can make an analogy to something that actually is moving in a circle, and as long as these two guys have the same period, those will be true. And let me just show you, let's focus on the velocity here. Let's focus on this mass spring oscillator, but not focus on the velocity itself, but not focus on the force itself and the acceleration, but the velocity. Come on, get rid of the forces. And add the velocity. Make them bigger. Okay. So, let me slow it down. So here, we should know, I'd start from the maximum negative amplitude, zero velocity. The velocity vector will grow until it gets to equilibrium, and then it will still be positive, but it'll start shrinking, because then the force reverses, so the acceleration reverses, so it shrinks until the velocity is zero again. And then it starts pointing to the left, zero at first, but then grows till it gets to equilibrium, and then it starts shrinking, and then it's just back and forth like that. It's a little complicated, but if you understand the nature of the acceleration and the force in this case, then it should be pretty easy to see. Right? So obviously this guy has got a velocity that obeys that type of a relationship. Zero there, maximum about there, starts getting smaller there, zero there, back and forth. If I go back to this guy, and instead of just showing his velocity, I show the components of the velocity. And you can focus on either. You can focus on the vertical component or the horizontal component, but you get the same kind of thing. And since we're talking about horizontal mass spring oscillators, look at the horizontal component of this guy's velocity. Here it's zero. At the maximum amplitude over here, it's zero. And then it grows and gets to a maximum value there. The horizontal component is now at a maximum. Let me slow it down a little bit. But then the horizontal component then starts to shrink. Becomes zero at the maximum negative extent, or the maximum negative amplitude, just like the mass spring oscillator. Grows as it's moving this way, maximum here, smaller. So this vector right here obeys, or it operates just like the velocity vector for the mass spring oscillator. Okay. So hopefully this is making it. And it's not just an analogy. It's not just an analogy. And this is a springboard to higher level physics thinking, mathematical thinking. And that is that whenever... Oh, let me get it. I'm sorry, before I get there. One other thing that should kind of drive this point home. This is a simulation on... on Pivot Interactives that we'll do a lab on next week, by the way. And I have a turntable that's just spinning in a circle, but they've taped a little piece of paper on the end of it so we can kind of keep track of it. Then we have a mass that's on the end of that's connected to two springs that are anchored, so it's going to oscillate back and forth. And they got a pendulum that's going to oscillate back and forth. And they made sure that the period, the time it takes for one complete oscillation, is the same for all three of these. And as you'll see, when this piece of paper, yes, it's moving in a two-dimensional plane at the same speed. But if we just focus on the horizontal component of that motion, or the x direction component of that motion, then it's moving the fastest when it's here, and then it stops when it's here, and then it's moving the fastest when it's here, just like the mass and the mass on the spring, and just like the pendulum. And so they're the same. You have the same motion, right? This guy, it's easy to see, has an angular velocity or an angular frequency because it's actually sweeping out angular measurements per unit of time. So we just make the analogy to these two guys and say, well, they have the same angular frequency. If this guy had an angular frequency of pi over 2 radians per second, we would say that these two had an angular frequency of pi over 2 radians per second. Now, looking at it in that way is analogous. That's an analogy, okay? Though we can actually, and this is what I was talking about, where once you get to a certain level of physics, engineering, when you put things on graphs, the things that you put on graphs, and we've already done this, the things that you put on graphs don't obviously have to represent things that exist in physical reality, right? Things that you can measure with a ruler. Yes, we can plot height versus length on a graph, but we can also plot velocity versus time on a graph. You can plot anything. And so what I could do is take this guy, this mass spring oscillator, let me get rid of these, and instead of just doing our motion graphs, which I will come back to in a second, I'm going to do something fancier. I'm going to plot the velocity of the object in the x direction. That's what this says if you can't read it. I'm going to plot the velocity in the x direction versus the position in the x direction. So now I'm plotting a more abstract type of a graph. I'm just plotting these two things that are describing the motion. And so if I think, well, it starts at a maximum negative position, and then it will, in the middle, and it has zero velocity, right? So I start at zero velocity, maximum negative position, and then eventually I'll get to the equilibrium position, in which case I'll be at the zero at equilibrium, but I'll have a maximum velocity, so the velocity would have increased by then. But then I start moving this way, and once I get to the maximum positive position, then the velocity comes back down to zero, but then I start going back. So it's not like a motion graph where the time is going to keep advancing to the right. No, once I start going back, it keeps clicking. Can we stop clicking, whoever keeps clicking? If I'm plotting it versus position, the position is going to be going back. We're coming back the way we came, right? It's never going to go beyond the maximum amplitude. It's going to start coming back. And if I do that, if I plot the velocity of this guy versus position, look what I get. So right here, equilibrium, maximum velocity. And then once I get to maximum amplitude, zero velocity. But now my position is coming back. The position of the object is coming back, and I start increasing my velocity, but in the negative direction, right? When I get back to equilibrium, I'm at my maximum negative velocity. And then whenever I get back to the amplitude, I get back to the starting position, same starting position, zero velocity. And so this object then, that's a circle, right? And so depending on what you plot, what physical quantities you plot, you get different shapes. And those different shapes can tell you different things. So you can make the analogy with an object moving in a circle to talk about the angular frequency of a mass spring system, mass spring oscillator. Or I could actually plot the velocity versus position. And from this, and we won't do this in this class, I'm just trying to give you a visual so that you can make the connections in your brain. You're not as confused as I was when I was learning about this. I can see a circle right here. And at this point, I will point out, in my opinion, one of the top, I'd say top 3 And especially if you're going to major in STEM, it's so much easier for you guys than it was for me because the YouTube wasn't what it was when I was in college, and I had to learn all this stuff from books, and it was so difficult. Nowadays, you can go on, and there's people way, way smarter than me, way smarter than a lot of college professors that create content that makes it so much easier to learn higher level stuff. This is one of the ones I recommend. He's got great playlists for learning calculus. If you're majoring in STEM, you're going to have to take linear algebra in college, which sounds like it might be easy. Linear, line algebra, we know algebra. Linear algebra is not easy. It is not easy. He's got a great playlist for linear algebra that I really recommend watching. But one of his videos, and I'll show it whenever we study momentum and collisions, one of his videos, he emphasized the point. And by the way, he used to be a Khan Academy creator. He did a lot of the higher level stuff, the college level mathematics and physics coursework for Khan Academy. Now he does his own thing. He is a super genius. He programs all of his own animations for his own videos. So he's an expert computer scientist. He's an expert physicist. He's an expert mathematician. I think mathematics is his real area of specialty. But one of his videos, and again, one I'll show you in a few weeks from now, he points out, anytime you see an equation that has a pi in it, even if it's something dealing with something that doesn't look like it's moving in a circle, anytime you see an equation with a pi in it, there's a circle associated with it in some way. Even if that circle doesn't actually exist in physical space, if you see a pi in an equation that talks about something, there's a circle involved there somewhere. As we'll see, the period, there is an equation for the period of a mass spring oscillator, and pi is in that equation. There is an equation that describes the angular velocity for this mass spring oscillator that's moving in a straight line. There's a pi in that equation as well. Where does that pi come from? Well, it comes from graphing its motion in this type of a way, where we actually see a circle. Circle doesn't actually exist, but we can see it graphically if we plot the right variables.
Because you only get a pi from a circle, right? You don't really get pi from...
Yeah. Pi is literally a ratio of parts of a circle, right? Yeah. Excuse me. So good point. And again, those of you going to STEM in college, 3 blue, 1 brown, definitely one of those YouTubers that'll help you. That'll make your life easier. You won't be like me, spending all your time studying when all your friends are out having fun because they majored in mass communications. Yeah. Okay. Not that there's anything wrong with mass communications, but you want a high-paying job, you'll major in something else. Okay. So there's that. Oh, one other thing. What time are we out of here? Oh, wait. Yeah, we're good. I want to go back to motion graphs briefly. Sorry. Okay. So here I got a position versus time graph and a velocity versus time graph. Oh man, we didn't start it. Yeah. So position versus time velocity. These are 3 kinematic graphs for simple harmonic motion. There is an equation on your formula sheet that is used to describe the position as a function of time. So I just want to show you that. We start at maximum, negative displacement, 0 velocity. And then I'm going to let the graphs go until we get to equilibrium, and then we'll talk about the graphs. So I let it go until we get to equilibrium, which is when the spring force becomes 0. Try about there. Started at maximum negative amplitude, maximum negative position, and then ended up at the 0 mark, which is our equilibrium position. Maximum negative position, we released it from rest, so we started with 0 velocity. But the force created acceleration, which sped the object up as it moved from equilibrium or from the amplitude to equilibrium. But the spring force got smaller, and so the increase in velocity got smaller, so the slope decreases as we approach that. The squeaking, can we stop the squeaking, please? And then once we get to equilibrium, we're moving at our fastest velocity, so we reach the apex of that curve, right? In that same time interval, we start with maximum force, so we start with maximum acceleration, but as the spring gets extended, the force gets smaller, and so the acceleration gets smaller, and when it gets to equilibrium, the acceleration is 0. Right? And so if I let it go again, we just get the mirror image of those on the other side of the axis. Right? And those in pre-cal know that these are cosine and sine graphs. This is a negative cosine graph because it starts at the amplitude, but in the negative side. This is going to be a sine graph because it starts at the origin. Positive because it has a positive slope. This is a positive cosine graph. Okay? The slope of this graph at any point is the value of this graph at the same point. The slope of this graph at any point is the value of this graph at any point. That's calculus. That's the derivative, which you all have learned or will learn next year. And if I let this go, we get 3, they call them sinusoidal graphs. That encompasses both sine and cosine. But they are not in phase with each other, right? They're all increasing and decreasing at different times. But they all look relatively the same general shape. They just, but if you understand, I get maximum position. Well, at maximum position, I have 0 velocity. At maximum position, I have maximum negative acceleration because we have a negative force. And that's when the spring is maximally extended, so you get the maximum spring force. So that's the kinematics there, and we do have one equation on our formula sheet that talks about the kinematics of motion graphs. All right. So let me tie it all up here. So hopefully that got you over this hurdle. Those simulations, those considerations. You can make an analogy between an object oscillating back and forth and an object actually moving in a circle. Or you can just see that depending on what quantities you plot that pertain to an object oscillating back and forth, you can get a circular graph. Okay. So the equations now for this unit that are on your formula sheet, and there will be one more for the whole unit, which we'll talk about tomorrow. Yes, sir.
Is there a symbol for angular frequency?
Oh, yes. I'm sorry. It's up there. I just didn't write it big enough. That is, remember yesterday when I told you guys number 14 on the quest assignment, which I'll remind you is due tonight. Number 14 on the quest assignment, all the answer choices with that roundy W, none of them are correct, so just ignore them. That's the symbol for angular frequencies. It's a roundy looking W. It's technically the lowercase omega. It's the lowercase Greek letter. This is the capital omega. That's the lowercase omega. Thank you, Mr. Francisco. Good. All right. So the equations, the ones we already know, Hooke's law. Hooke's law. This is how it's written on the formula sheet. But please understand that if we talk about, this means magnitude. The magnitude of the spring force is equal to K times the magnitude of the displacement. If you got a free body diagram and you have a spring force, just if it's up, it's positive. If it's to the right, it's positive. If it's down, it's negative. To the left, it's negative. But the big kid version, the big kid picture, you got that negative there. Telling me that whatever direction my displacement is, the force is going to be in the opposite direction. That's what that negative is there for. But most of the time, you just use your free body diagram, and then this expression, you can kind of ignore the negative in this and just use your free body diagram to tell whether it's positive or negative. If you stretch a spring a certain distance x or compress it a certain distance x, you store spring potential energy. We already know this equation. It's 1/2 k times the displacement squared. Yes, x is a vector, but when you square it, it actually becomes a scalar for reasons that you'll learn about when you take vector calculus in college. Those are the two we already know. And we know that the period and the frequency are inversely related, according to this, but on the formula sheet, it shows the relationship between period, frequency, and angular frequency. And it looks like this. Period t equals 2 pi over angular frequency, which equals 1 over the frequency. Those of you in pre-cal have seen this. Y equals a cosine bx plus c plus d, right? The general form of a cosine or sine equation. Well, how do you get the period from this? What's the period of a sine graph? Or cosine graph?
Is it D?
No, d's vertical shift.
C.
Like,
You guys not get here yet?
like 2 pi over
A is the amplitude. What? Alex?
I mean, it's like, I know I'm on something. It's like 2 pi over, is it 2 pi over the period? Or
Yeah, the period is 2 pi over the coefficient in front of x.
that's what it is.
Yeah.
Okay, I was
2 pi over b is the period in your math class. 2 pi over omega is the period in physics. So literally b tells you the angular frequency of your sine or cosine graphs in pre-calc. Okay. So that's no accident that it says period is 2 pi over omega. It's the same thing as in pre-calc. Okay. Only now we're using it to describe, using what you learn in pre-calc to describe physical reality. What else is on the formula sheet? The period for a mass spring oscillator is equal to, and notice the pi here, right? The pi with the omega. That means omega is a circular thingy, right? It's a spinny thing. Even if you have something that's not actually moving in a circle, that pi there tells you there's a circle involved with it somewhere, right? Whether it's obvious. Kurt?
No, I
Okay.
just wanted to make sure that I had the right line.
Okay. And so the mass spring oscillator period is going to be 2 pi times the square root of the mass that's attached to the spring divided by the spring constant K. As is often the case, you see that equation, you wonder where it comes from. What do you have to do? You want to know where it comes from? You have to, next year, take AP Physics C. See that a lot?
No, I looked it up.
Well, you can look it up, but if you're like me, you want to know where it comes from. They didn't just make this up. This is actually
That's what I'm
derived.
saying. I looked up why it is that. Why?
Oh, okay. There you go.
That's interesting.
Well, okay.
Wasn't it? It was just, yeah.
Well, it involves
Exactly,
calculus.
but isn't it-
Involves some pretty tough math, but anyway.
I just
So that's the period for mass spring oscillator. If you know the period, or if you know the mass or the spring constant K, you can figure out the period, which you can then use to figure out either the angular frequency or the frequency using that equation. Now the position function, as it's written on the AP Physics 1 formula sheet, and I don't like how it's written because it's not... Yeah, this is how it's written on the formula sheet. It doesn't jive with your pre-calc class, so I don't like the way that the College Board has written this equation on your formula sheet, but we can adjust it by using this relationship up here. But the College Board on the AP Physics 1 formula sheet that says that the position function x equals the amplitude, same amplitude as up here, but now it's like the physical distance, the literal distance in meters, times the cosine. And we use cosine when we start from the amplitudes, right? If we stretch the spring and then release it from the amplitude, it's going to be a cosine graph. So it's going to be a times the cosine of 2 pi times the frequency, not the angular frequency, but the actual number of oscillations per second, times the time. If you do it this way, your answer, or you're going to want to be in degree mode. And when you go from this equation to what I think is the better way of writing this, because it does jive with your pre-calculus class, I can replace f with 2 pi with omega over 2 pi, right? If I can solve this equation for frequency, and it will end up being omega angular frequency over 2 pi. And if I plug that in for this guy, the 2 pi's will cancel, and so I just end up with omega times t. This is not on the formula sheet, but I feel like it should be in this way because it does jive a little more with what you see in pre-calc. So you have position is equal to the amplitude times the cosine of omega times t. And again, t is our variable. T is our variable on our horizontal axis. X is our variable on our horizontal axis for your sine and cosine graphs in pre-calc. X is our position. Y is our vertical position on your xy axis. Y is a function of x, right? So I like thinking of this as x being a function of time, where x is literally our position. Remember, our position never goes beyond the negative amplitude or the positive amplitude, so it always oscillates back and forth. Regardless of which one of these you use, let's say you want to know exactly where you set a mass spring oscillator going, and say there's no energy loss and it just goes forever. and you want to know exactly what position that object will have on between the two amplitudes at some time t, say 117.3 seconds from now. Then you put in 117.3 for t, or for t in one of these. If you know the frequency and the amplitude, then you can actually determine exactly where that object will be as it's oscillating back and forth at any time that you want. Okay. The last thing I'll leave you with, and this will be a question that we'll talk about tomorrow. We're going to finish the example 1 tomorrow that we started last week, I think. And that is, what if I change the amplitude? What happens to the period? I'm going to change the amplitude of my mass spring oscillator. What are you doing back there, Jacob? You haven't looked up in a while. What are you still doing? You're not on your phone, are you? Are you lying? Okay. You know this stuff that well, you don't need to pay attention?
Yeah, pretty good.
Okay, I'm going to hold you to that. Okay, so this guy oscillates back and forth. Not this one. I get a certain period, right, with a certain amplitude. Now I'm going to change that amplitude. What's going to happen to the period, Jacob? I change the amplitude of the mass. What's going to happen to the period? Huh?
Decrease it or increase it?
Neither. I thought you knew this.
You change the amplitude?
It's going to be the same. You change the amplitude, the period's the same. The time it takes for this motion is the same as the time it'll take for that motion. Same time. How do I know that? You guys can leave. How do I know that? Amplitude's not in the period equation. The amplitude does not determine the period. You pull it farther, it's just going to be moving faster. It'll have the same amplitude. Have a good day. Awesome, Indiana.